Hey, welcome back, my little arthropods. Today we are on our last lesson for graphing. Huzzah! Congratulations! Woohoo! Go ahead and tell your parents how happy you are. You made it, right? They ought to have like a little graduation ceremony for you guys, and they should throw like little shredded pieces of paper with graphs on it and be like, "You're done graphing." If you're a senior, this might be your last graph ever. Isn't that exciting? So we're going to do some graphing today. All right, so let's go talk about graphing our reciprocal trig functions. But first, we need to remember what a reciprocal trig function even is. So there are three of them. There is cosecant, secant, and cotangent. And remember, they're kind of mixed up. So cosecant, you would think it goes with cosine because that's what makes sense. But I think whichever mathematician came up with this had been like drinking a little bit too much when they did it. So cosecant goes with sine and secant goes with cosine. And then for some reason cotangent goes with tangent, but like, sure, I guess. So they are literally just reciprocals, meaning cosecant is 1 divided by sine. Cool. So if we want to get our values for these reciprocal trig functions, what we can do is multiply both sides by the bottom one, so sine in this case. And then to get rid of the cosecant, we divide both sides by cosecant. So the sines cancel, the cosecants cancel, and we get sine equals 1 over cosecant, right? So if I want to know cosecant, right, it's just 1 divided by that sine and vice versa, right? So we can go back and forth by just flipping these. Cool. So if we want cosecant, the way we're going to get that is we're going to take the value of the sine function and divide 1 by that number. Okay, so let me show you how to make this first for the cosecant function. Then, in the interest of not wasting all your time, I'm going to just show you a picture of secant and cotangent because it's pretty much the same thing. Then we'll do 2 examples of like if they have transformations, but we're going to keep it pretty simple, and you won't get an example of graphing cotangent just because graphing tangent is bad enough. There's not, you know what I mean? Just count your blessings, right? Or something like, I don't know. Be grateful. All right, anyway, next slide. So we are going to graph the parent function of cosecant. So before we do that, let me go ahead and graph sine really quick. So we're going to graph sine, and that's going to make it really easy for us to graph cosecant. Okay? So let's do sine in red, and then I'll do cosecant in blue. So here we go. All right, so sine, we all know sine starts at 0. At pi over 6, sine is a half. Then at pi over 3, it's 0.7, almost 1, right? Pi over 2, or 90 degrees, sine is 1. Then it reflects back down. And then at pi, we're back at 0. And then it's just this thing but reflected, right? So we're going to go negative a half, negative almost 1, negative 1. And excuse me if these aren't perfectly in the right spot, but our sine graph is going to look pretty much like that. All right, so let's write down a couple important values here, and then we'll do our reciprocal of them. So sine of 0 is 0. Sine of pi over 6 is really easy. It's a half. Sine, I'm going to skip pi over 3 because it's kind of ugly. I don't want to deal with radicals. This is just to give you the idea. So pi over 2 is 1. And then we'll just use these values to guesstimate the rest of cosecant. So cosecant is 1 divided by sine. So what we're going to do is for cosecant, of these. So cosecant of 0 is 1 divided by the value of sine at that same angle. So 1 divided by 0, this is undefined. Okay. So our first one's undefined. The reciprocal of 1/2 is 2, right? 2 over 1. And then the reciprocal of 1 is 1. So cosecant of pi over 2 is 1. So let's go put these three values on our graph. So here at the 1/2, our cosecant is going to be at 2. When sine is at 1, cosecant will be at 1. So at 1, we're at 1. All right, here's our 1/2. Go back up to 2. And then when sine is at 0, 1 divided by 0 is undefined. Anytime you have undefined, what that means is you have a vertical asymptote. So we're going to have our vertical asymptote. Let's make it blue. Here, anytime it crosses the x-axis. So here, here, and here. Come on. Why did it change? Technology, you guys. I dream of a world where my programs work correctly. So, all right. Holy smokes, you guys. I'm a professional, I swear. Okay. All right, so there's our asymptotes. Now, if we look at some of our negative values, here we have sine of 7 pi over 6 is negative 1/2. If you reciprocal negative 1/2, you just get negative 2. So cosecant of 7 pi over 6 is just negative 2. So what we see is that we get the same values, just negative because of the negative, right? So we get negative 2, 0, negative 2. Can you guys kind of see what's going on here? So as you divide 1 by smaller and smaller numbers, it gets bigger and bigger. So what's going to happen is you're going to get a graph that looks like this. Whoops, I missed a little bit there. And then where sine is below the x-axis, or it's negative, you get the same thing just reflected. There you go. So for cosecant, what we're getting are repeating u's and upside down u's. And what's important to notice is that, let me just change the color really quickly. Where sine and cosine have amplitudes, where it never goes above this value or below this value, those amplitudes kind of turn into like a no-fly zone, if you will, or a no-graph zone. For their reciprocals, your reciprocal functions will never go inside the amplitude of its corresponding function, right? So if you want cosecant, what you do is you pretend that it is sine, graph that sine function with the same amplitude, same period shift, same vertical and horizontal shift. Anytime sine crosses its midline, you get a vertical asymptote. And then you put your cosecant u's and reflected u's so that they just barely touch at the mins and maxes, and they have to stay outside of this kind of forbidden zone in the middle. Cool? So let's go look at secant. So here, this dashed green line is our cosine function. That's this thing here. We can tell because it starts at a maximum and then it does its full period by 2 pi. So for our secant function is basically the same thing as the cosecant function. It's just because cosine is a little bit shifted from sine, secant is a little bit shifted from cosecant. So it looks the same. You still have your vertical asymptotes. Wherever cosine would be 0. So cosine is 0 at pi over 2. You can see vertical asymptote. Cosine is 0 at 3 pi over 2. vertical asymptote, and so on, right? And then this repeats. We do have the same period for secant as cosine. Here is half an up, a full down, and then the other half of our up, and then that finishes at 2 pi. So the period for secant and cosecant is still 2 pi. Horizontal shifts and all that stuff still work the same way. Vertical shifts still work the same way. Reflections still work the same way. The only difference is if you change your quote-unquote amplitude, or the value of A. So if we have y equals A secant of x, this A value will just move your cosine so it's taller. It would be more like this. Hold on, I can't graph. Ooh. Right? And then your secant will just stay outside of that zone. So it makes kind of the forbidden zone in the middle between your u's a little bit bigger. Cool. All right. Now our last one is cotangent. This one is going to be kind of weird to look at, but I'll do some drawing on the graph and explain it. So here is cotangent. And you're going to say, Barton, this just looks like tangent, but like flipped over. And you're right. So for cotangent, let's maybe check out our tangent graph. And then we'll try and analyze why this happens. So for one section of our tangent graph, it'll look like this. Okay. So when tangent of 0 equals 0, that means if we take the reciprocal of this, cotangent of 0 is 1 over 0. So we get a vertical asymptote like that. Okay, great. Now, when cotangent is when tangent is really small, so let's say tangent of like 2 degrees, we'll say that's like 100 per se. Well, it probably isn't, but you know, we'll guesstimate it, right? That tells us that cotangent of 2 degrees is 1 over 100. So when tangent is big, cotangent is really small. Likewise, where we have a vertical asymptote for tangent, tangent of 90 degrees is undefined because it is 1 divided by 0 if we go off the sine over cosine, or y over x. So if we do the reciprocal of undefined, we have to remember where the undefined comes from. It comes from this fraction. So if we do cotangent of 90 degrees, we're just flipping this fraction. We're doing x over y. So it is 0 over 1. So anywhere you have a vertical asymptote for tangent, you get a 0 for cotangent. And then here on our tangent graph, it would do, let me just put in another asymptote. It would do something like this. So where we have this whole negative section right here on our tangent, we still have the same negative section for our cotangent. So they look very similar. It's just anywhere there was a vertical asymptote, now there's a 0, and anywhere there was a 0 for our old graph, now there's a vertical asymptote. So it has this kind of look where it's just flipped over. So instead of this, it's kind of like that, going the other direction. And it kind of looks like the whole thing has been shifted over pi over 2. Cool. So tangent and cotangent, very, very similar. You can turn tangents into cotangents really easily, but you know, if you're into that sort of thing. So, all right, let's look at a couple of examples of graphing cosecant and secant, since I think they're the more interesting graphs anyway, and they're gonna be I don't know. I like them better. That's why. So let's go ahead and try and graph this. We have y equals -2 cosecant of x minus pi over 6. So the way you're going to graph this is you are going to pretend for right now that this is its reciprocal function, sine. Pretending. Okay. So we don't have a k value, so our midline is still going to be at x. Oh, that's ugly. Let me get a real midline. Let's get red. Let's get a dashed line. We have our midline on the x-axis. All right, wonderful. Our amplitude that's not what I want. Our amplitude is equal to 2. Remember, it's the absolute value of A. So we're going to go up 2 from the midline, and we're going to go down 2 from the midline. And let me just adjust that so it's a little bit more measured. There we go. And then because we have this negative, we're going to reflect it over the midline. Okay. Lastly, this h value, h equals pi over 6, tells us that we're going to translate to the right pi over 6. All right, so now we're ready to graph sine. Sine, of course, starts on a midline. So our first point, let's do it in blue, starts normally at 0, but remember we're going right pi over 6. Then it goes up to a half, but times 2, of course, so up to 1. Almost up to its maximum, back down a little bit, a half, midline, 1, 2, 3, right? 1, 2, 3. Down to the minimum, back to 0, half, and then we have our sine function. Okay, so that's about what sine, or y equals -2 sine of x minus pi over 6 would look like. The reason we want this is because this will give us a good guide for our cosecant graph. So now let's do cosecant, how about green? So anywhere that sine equals 0, right here, right here, right here, cosecant will be undefined. So everywhere our sine graph touches its, whoops, excuse me, sorry, there we go. Everywhere it touches the midline, we're going to put a vertical asymptote. Vertical asymptote. Vertical asymptote, vertical asymptote. There we go. And then the way you make your cosecant graph is you make sure it touches right there at your maximum, touches at your minimum, and then it's going to make a big U in between your vertical asymptotes. So then this is pretty much our graph for our cosecant. So the trick is graph sine, put your asymptotes wherever it touches the midline, and then put u's that just touch at the tops and bottoms. Cool. All right, let's go ahead and do secant just to see another example of the other inverse trig function, and then we're not going to worry too much about cotangent because, you know, cotangent. So, similar strategy here. We're going to pretend this is its reciprocal, which is cosine. So we're going to have an amplitude of 3 because of this. Our period is adjusted because of the b value. So our period is equal to 2 pi over b. So it's just regular pi. Our midline is going to be at y equals 1. And then we don't have any horizontal shift because there's no h value here. So our graph is going to get squished a little bit in the horizontal direction like that because of this b value. And we're going to have an amplitude of 3. So let's go ahead and graph the cosine function, and then we'll use that to get our secant function. So let's put in our midline. Let's make it blue. Let's make it a dashed line. So midline at y equals 1. Our amplitude is 3, so we're going to go up to 4. That's our max for our cosine function. We're going to go down 3, 1, 2, 3. And that's going to be our minimum for our cosine function. Just make sure that's in the right spot. Okay, pretty good. And then our period is going to be pi. So for cosine starts at a maximum. At the end of its period, it's going to return to the maximum. Halfway to the period, so half of pi, it will be at the minimum. And then halfway between this maximum and this minimum, so 1.5, we're going to be on the midlines. So our cosine graph is going to look pretty much like that. 1, 2, 3. Min. 1, 2, 3. Max. We'll just do 2 full periods just so we can really see the features of secant. And it might be prudent to maybe graph a little bit on the negative side as well. Okay. All right, so here's our cosine graph. Now, it's really easy to turn this into our cosecant graph. Let's go ahead and do red for our cosecant, or for our secant, excuse me. So, again, anywhere you touch the midline, you're going to have a vertical asymptote. And you're going to say, but Barton, it doesn't equal 0 here. Shouldn't it be there where the x-intercept is? Not quite. The reason you get the vertical asymptotes is not because y equals 0. It's because cosine equals 0. So it doesn't really matter if we shift the graph up or down. Anytime the trig function would be 0, the reciprocal of that trig function would be undefined. So it happens anywhere there's an intersection between the graph and your midline. So on your midline intersections here, you're going to put your vertical asymptotes. I'll move that one. I'll move that one too. And that one as well. Let's see if I can hit this one. No, not too bad. All right. So just put these back where they belong. Scoot them over. Okay. Now, just like we did for our cosecant, for secant, you just want to make sure that you are hitting the mins and maxes of your cosine or sine function. And then you get these nice looking u's in there. And then if we were being really, really careful, this is more of a sketch, honestly, because I'm not actually plugging in the values and doing the multiplication for the amplitude changes. We should, if we wanted it to be, if you were going to get this published in like a journal or something, or your boss made you do it, and lives depended on this, then yeah. But for this homework assignment, it's not that serious. I'm not going to drive to your house and like harm your dog or your family if you don't get the values exactly right. The important bits are you get the distance between these and these correct. You get the amplitude, quote unquote, correct. You get the period correct, and you get the approximate placement correct. It's not a huge deal if this should have been there. I'm not going to drive to your house and like beat down your door and then steal your Nintendo Switch and delete your Animal Crossing save file or anything crazy like that, you know? So, all right, so there is graphing reciprocal trig functions. Hopefully that's not too bad. Hopefully it's just more practice graphing parent trig functions. But if you had any questions, or I went too fast, or you think, you know what, Barton, you're just not a very good teacher, go give me a piece of your mind. Join the WebEx. Let me know what your voice sounds like. Anyways, until next time, have a good day.